Alright guys, we didn't finish the lesson in class, so I wanted to record this video to finish 5.3 with you, but also to go over 5.3 again so that in case you missed out on anything, you can fill it in right now. In 5.3 we talk about a few properties of integration, and ultimately integration is a way to find areas under a curve. So for example, the first few properties involve the area of a function between a and b. So say if you have a function and you basically want to find the area between a and b of that function, then it turns out that when we write this symbol, the integration between a and b of f of x dx, it is the same as putting an extra negative in the front if you were to switch the lower bound and the upper bound. So b from b to a, the function dx. If you're integrating with a constant, you can pull the constant out, okay, so that you don't have to worry about that as part of your integration. The integration of the sum or differences of two functions is equal to the sum or the differences of the integration of each function. Like that. Okay. And then now this one is a little interesting, and we kind of talk about this in class, but I'll go over it again with you. If you are finding the area, say if you have a curve and this curve runs from A to B to C, so if we look at the first instance where this is the area from A to B, the area from A to B, and then the second integration expression, it represents the area from B to C, and we're adding those two together, and if you add those together, then that's the same as saying I'm looking for the area from A to C, okay, from A to C, fx dx. Alright, and then the last one over here, and this one I kind of went through it kind of fast. Basically what I'm saying here is if we're given a function between a and b, and say if this was the function, right, then what this says here is the area between the curve, the area between a and b, will be less than the maximum value of the function. So here's the maximum value of the function, right? And the maximum value of the function times the length of the function, the length of the interval, I'm sorry. That, you can think of that as the area of a rectangle, because here's the length, okay, and the maximum value of the function gives you the width. Okay, so that's really a rectangle, and notice that the area of the rectangle is more than the area of the curve, so that's why it's larger than the area of the curve. And also, if you look at the minimum value of the function, which happens right here, that's the minimum value times the length of the interval. Here's the length of the interval. If you multiply those two together, you can think of it as the area of a, once again, a rectangle, a smaller rectangle that's less than the area of the curve, as you can see. So I hope that helps. Now we're going to apply some of these properties and try to evaluate some of the integral expressions here. So given that the integral from 1 to 9 of f with respect to dx is equal to -1, the integral from 7 to 9 of f of x with respect to dx is 5, and then the integral from 7 to 9 of h of x with respect to dx is equal to 4. So h and f of x are two different functions. Alright, so when we evaluate number 1, we notice that there's a constant in the front, so first thing I'm gonna do is apply the second property to pull out the constant. Okay, and then we're given that that's equal to -1, so we take -1 and we replace it for that expression multiply that by -2, and you end up with 2. So that expression is really the same as 2. Okay. Now this expression right here from 1 to 9, well, that's just equal to 1. I'm sorry, equal to -1, because that's what it says. Now the expression from 1 to 7 is a little tricky. Notice that you know the area, or you know the value from 1 to 9 of f, but not from 1 to 7. But you know that 1 to 7 is between 1 to 9. So the trick is to break that up. So you can go the integral from 1 to 9 of f with respect to dx is the same as saying the integral from 1 to 7, because 1 to 7 is between 1 to 9, plus 7 to 9. Alright? And because we know what 1 to 9 is, that's -1. We're looking for that, so you can leave that alone. And then you know what this is. This is 5. So if you subtract 5 to both sides, then you're going to see that the integral from 1 to 7 of f is equal to -6. So that's why that's -6. Alright? Good job. And then to evaluate 4, we use property number 4, which says that the integral of the sum is the sum of the integral. I'm sorry, property number 3. Right? So we're going to go ahead and rewrite it as 7 to 9 f plus 7 to 9 h. And this value is 4. I'm sorry, that value is 5. It's 5 is right here. Okay. This value over here is 4, because that's right there. So you add it together, you get 9. Okay, good job. Now, a function that we kind of skip over, or not a function, but a theorem that we kind of left out, and then we move on to the next page, is the average value. Okay, the average value. The average just basically means the average. And so here we're looking at the average value of a curve, in a sense. The average value, the definition of the average value is right here. The average value is defined as the area of the curve, which we can find using the integral divided by the length of the integral. Oh, I'm sorry, divided by the length of the interval. Okay, so here is the length of here's the width, or the length of the interval. That's the width. And then, so that's at the bottom, as you can see. And then here's the area of the curve, the area under the curve. Alright, so here, if you want, you can also write it like this: the area of the curve. Okay. Divided by the width, which is b minus a. Right, so that two expression would really mean the same. Right? Basically, what average value is, it's a number. This is going to be a number. This is a number. Okay. This is a number such that if once you find that number happens to be, if you take that number and multiply it by the width, then that number times the width will yield the same area as the area under the curve, and we call that number the average value. Right? So for now, just remember that the average value is the area of the curve divided by the width. That's the average value, or this is the symbol that we use for the average value. Alright, now we're going to flip the page, and from knowing the average value, how to find the average value, we're ready to introduce you to the mean value theorem for integrals. Recall before this section, we had the mean value theorem for function, we had the mean value theorem for derivative, If you don't recall what those are, you can always review your notes to figure out what they are. But now we're looking at the mean value theorem for definite integrals. So here's what the mean value theorem for definite integrals basically tells us. Basically, if you have a function that's continuous from a to b, okay, and I'll draw it for you, from a to b, okay, you have a function that's continuous from a to b, right? Then the mean value theorem guarantees that there is some point C between a and b. So there's some point C, okay, between a and b, okay, such that the function evaluated at that point is the same as the average value. Same as the average value. In other words, there is some point between a and b such that that point is really the average value. Okay. And what that also means is if you were to find the area, if you were to take that function value and multiply that by the width of your interval, then the area that you get from that rectangle will be the same as the area under the curve from A to B. Alright? So the mean value theorem basically guarantees us that we can find the average value of a function the mean value theorem basically guarantees that there is a point between A and B within our domain such that f evaluated at that point is the average value. Right? So you can find the average value because you know how to find, say if you know how to find the area under the curve, take that value divided by the width, then that gives you the average value. And the mean value theorem once again just basically says that you can also find the same value by evaluating the function at a point between A and B. So I'll take you through a problem that deals with the mean value theorem. So use your calculator to find the average value of the function. Then find C where the average value would exist. Right? So first of all, I'm going to go ahead and find the average value of the function. And we're using a calculator. So first of all, the average value would be equal to the area from 0 to 3 of my function x squared over 2 dx. Divide that by the length of the interval, which is 3 minus 0. So the way how you would find the area using a calculator is you would push the button math and then choose option 9. Okay, hit on the number 9. And this will kind of show up, and then we're gonna go ahead and we're gonna type our integral. So the integral will be from 0 to 3, and then the function is negative x squared. Okay, so negative x squared, divided by 2, integrating with respect to x. Okay, and push enter. So the area under that curve is going to be negative 4.5. And now I keep using the word area, but this integral from now on is just going to be a net value. Unless the problem specifically tells us to find the area, then we'll find the area. But from now on, whenever we evaluate an integral of a function, then the value that we'll get is just going to be whatever value it comes out. But if I mention like the word area, then you want to, you know, change that to a positive number. But anyways, for now, that number is just going to be negative 4.5. So I know that this number here is going to be negative 4.5, and I'm going to divide that by 3. So divide that by 3, that's going to give me negative 1.5. So that's equal to negative 1.5. So the average value is negative 1.5, and the mean value theorem guarantees that there is a C, there is a number between 0 and 3 such that f evaluated at that number is also negative 1.5. And so find that C. So what we're going to do is we're going to go, there is a C that equals to negative 1.5 because the mean value theorem guarantees us that. So we go ahead and we replace this for our f of c, so that's going to be negative c squared over 2 equals to negative 1.5. Multiply both sides by negative 2. You want to get rid of that. So c squared is equal to, if we take 2 times negative 1.5, that's going to give us 3. So c is going to be plus or minus root 3, right? And because negative root 3 is not in our domain, we only count root 3. So look, f at root 3 is also negative 1.5. And if you want to check, you can. Look, 3 squared divided by 2, and remember there's a negative in the front. Second, insert negative, right here, negative, and look what I get. I get negative 1.5. Okay, so there's a C, and I found it. So again, the mean value theorem basically guarantees that you can find the average value by evaluating your function at some point between 0 and 3. Okay, now, so that's the mean value theorem for definite integral. It's a pretty big theorem, and we're going to go back to that a little bit later. But what's also big is being able to continue to develop our skills on how to find areas of different types of function. So before we develop that skills, the next thing we're going to do is we're going to look at the connection between differential calculus, which is taking derivative, and integral calculus. How are these two related to each other? Well, the derivative, or scratch that. The fundamental theorem of calculus comes in 2 different parts. We're going to put part 1 in this box. So fundamental theorem of calculus part 1. And part 1 basically says that think of this as a function. Think of f of x equals to, think of the integral as a function. Okay, that's going to be a function. So this is going to return some value, right? So like if you plug in 2, if x is 2, f of 2 is going to equal to a number. So think of that as a function. Okay, f of 10 is going to be a number. F of a, if you plug f of a in here, then that's like saying find the area from a to a, and clearly from a to a is 0 because you don't have a width. Okay, so think of it as a function. But here's what the fundamental theorem of calculus part 1 says: if you take the derivative of this, okay, so let f go to that, then the derivative of that, the derivative of this, the derivative of that is just going to equal to f of x, whatever that is. Okay, f of x. And in general, okay, d with respect to d x, say if this was not x but at u, and u is a function of x, f of t dt, then that would be equal to f of u times u prime. If this was, like, for example, 2x, then this would have been f of 2x times 2. Alright, so that's why I use the letter u times u prime. Now, so that's fundamental theorem of calculus part 1, which says think of the integral as a function, and then all these are true. If you take the derivative, you get that. Now, FTOC, fundamental theorem of calculus part 2, okay, basically says that if you're evaluating, and this talks about evaluating areas. If you're finding the area from A to B of some function, okay, then it turns out that that is the same as evaluating big F at B minus big F at A, where big F is the antiderivative. Big F is the antiderivative. Alright? So, let me take you through a few problems that involve fundamental theorem of calculus part 2. So, here's the first one. In this case, we're just, and I'll draw a diagram for you. We're looking for the area of cosine from 0 to pi over 2. So, 0 to pi over 2 looks like this. Okay, so that's the cosine function, and cosine of course looks like that. But here's pi over 2, so we want to find this area. Alright. Now, as you can see, that's not easy to find because this curve it's curvy. The graph is curvy. It's not straight. It's not a shape that we know, so we can't really do it by applying one of the formulas. So what we're going to have to do is we're going to have to use the fundamental theorem of calculus part 2, which says that you can find the area if you know the antiderivative of cosine. In other words, what's the function? What is a function such that when you take the derivative, you get cosine? And f is the antiderivative. So the function is actually sine. The original function is sine. So, because if you take the derivative of sine, you get cosine. So once you know the original function, then you can find the area, or you can evaluate this integral, because according to this, it's just now equal to f evaluated at b minus f evaluated at a. So this is going to become sine evaluated at pi over 2 minus sine evaluated at 0. And we know that sine at pi over 2 is equal to 1. Sine at 0 is equal to 0. So the area under that piece is actually equal to 1. Okay, now when you're dealing with a power function, make sure you pull out any constant before the integral. Okay, and basically our small function is x squared. So what is our big function? What is the big F? Big F is the antiderivative of this function. Right? To find big F is actually pretty easy when you're dealing with a power function. Basically, you add 1 to the exponent. So I add 1 more to 2, and then I divide it by the same number. Okay, that's big F. If you look carefully, if you take the derivative of big F, you're going to get small f, and that's why they're called antiderivative. So to evaluate this, we're just going to now plug in, so it's now big F at 2 minus big F at negative 1. See? So big F at 2 is going to be, if you plug 2 in there, you're going to get 8 over 3. So 8 over 3 minus, if you plug negative 1 in there, you're going to get negative 1 over 3. And therefore, you're going to add and thus divide, and it comes out to be 3. Okay? Good job. Now, for trig, you just kind of have to remember some of the formulas. If your function is secant squared, then the antiderivative of secant squared is actually tangent, because the derivative of tangent is secant squared. So big F is actually tangent. So now, you know that what the antiderivative is. We're just going to go ahead and evaluate the antiderivative at pi over 4. Take away at big F at 0. Tangent at pi over 4 minus tangent at 0. Tangent at pi over 4 is 1. Tangent at 0 is 0. So therefore the answer is once again 1. Okay, or the area from under that curve is 1. Now going over here, your function is equal to 8. The antiderivative of 8 is going to be when your function is a constant, then the antiderivative is basically add in an x in front of that constant. Because look, if you take the derivative of this, then you get that. See? So now you're just evaluating big F at 7 minus big F at 3. Big F at 7 is going to be 8 times 7 minus 8 times 3. So in this case, 56 minus 21, you get 35. Okay, so the error is 35. Okay. Moving over here, now your function here, your little function is 1 over x. That's your function. So what is the antiderivative of 1 over x? In other words, what is a function such that when I take the derivative, I get 1 over x? Right? And it turns out that this is a special case. It's actually ln of x. Okay, ln of x, take the derivative of ln of x, you get 1 over x. So now that you found the big F, you're going to go ahead and plug in e, and then plug in 1. So this is ln of e minus ln of 1. ln of e is equal to 1, and ln of 1 equals to 0. So this is once again equals to 1. All right. This is the one that's referring to the fundamental theorem of calculus part 1. So don't forget that. The derivative of the integral. And notice that you recognize FTOC part 1 if either the upper bound or the lower bound is a variable. If they are both constants, if they're both numbers, then it's really part 2. If one of them is a variable, then it's part 1. Okay, so be careful. So the derivative of that integral is just the function, it's just the integrand, it's just inside. So the answer to this problem is actually pretty easy. So if you don't remember, look back at the definition over here. So it's just x squared minus tangent of x plus square root of x plus 1 minus 4, and you're done. Alright, very good. And I think that's all we're going to talk about today. If you have any questions, send me an email. Look over this video again, and if there's any part that you don't understand, make sure you come and talk to me. I will see you guys on Wednesday.